Welcome protein coders, let's build some coding muscles. Today we're going to start our DP concept playlist. We will learn about various concepts of dynamic programming through solving various problems. Okay, so without further ado, let's solve our first problem today, which is on Fibonacci series or Fibonacci series. So by definition, the nth Fibonacci number is defined as n is equals to 0 when n is 0, 1 when n is 1, or for else for n greater than or equals to 2, it is f of n minus 1 plus f of n minus 2. So it will be 0, 1 and then the sum of previous two numbers. So 1, 2, 3, 5. So if I write a recursive solution for this, it would be very simple. Let's take a function fib, which will take the integer n. For base case, if n is less than or equals to 1, it will return 1 at 0. Or else it will return fib of n minus 1 plus fib of n minus 2. And if I draw the recursion tree diagram for this, you can see f of 5 will call f of 4, f of 3, f of 4 will call f of 3, f of 2, f of 3 will call f of 2, f of 1. At the end, we reach the base cases f of 1, f of 0. And from here, we will return, right? And again, f of 4 will call for f of 2, f of 1, f of 0, and similarly. So from the base case, we will return, right? 1 and 0. So f of 2 will become 1 plus 0 equals to 1. And then again, f of 2 and f of 1 will return 1 and 1. So f of 3 will become 2. But if you see carefully in this recursive tree diagram, we are solving f of 2 multiple times. And similarly for the case of f of 3. So in such cases, when we have multiple overlapping subproblems, we use memoization. In memoization, we allocate a space based on the input variable. So suppose here n is the single variable, so we will take a 1D space, a vector, and whenever we solve a subproblem, we will store it in the vector. So if we again encounter this subproblem, we will not call the recursive call, we will return the value from the DP vector only. Okay. So for the case of f of 4, it will call for f of 3, but for f of 2, it will get the value from the DP vector. So in the code, there will be some minute changes. We will pass a DP vector also. And before returning, we will store the value of the recursion in the DP vector. And before returning, we will check if the DP of n is not equals to minus 1. That means we have already calculated the value for this subproblem, then we will directly return from the DP vector. Initially, the DP vector will be initialized by all values by minus 1. Okay, so what 3 steps we have done in memoization is creating a DP vector. The dimension will be based on the inputs. Second, we will check if the subproblem is already calculated or not. If so, then we will return the value from the DP vector. And the end, storing the subproblem answers in the DP vector. That's it. Now we have a third approach, which we call tabulation. In tabulation, we don't use recursive stack. The tabulation is actually the opposite of the memoization. In memoization, we have a bigger subproblem and we move towards the base case, and from base case, we rebuild the solution. That's why it is also called top to bottom approach, top down approach. We are moving from a bigger problem to the base case. While in tabulation, we move from the base case towards building the solution for the bigger subproblems. That's why it's called bottom-up approach. From bottom, we build the solution. So similar to memoization, in tabulation, we will have a DP vector and every DPI will represent the Fibonacci number at that index. Okay, so we will have a DP vector, and from the base case in the memoization solution, we can have that DP of 0 will be 0 and DP of 1 will be 1. Right? We can get that from the base case of the memoization solution. And for calculating the further states in the DP vector for tabulation, I can take help of the recursive solution or recursive relation in the memoization solution again. So I will run a for loop from int I equals to 2 because I 0 and 1 are already calculated till n, and I will write dp of I equals to dp of n minus 1 plus dp of n minus 2, which is very similar to the recursive relation which we have here in a recursive solution, right? And at the end, I will simply return dp of n because my answer to the nth Fibonacci number will be stored in the nth state of the dp vector. So initially we will have 0 and 1 for 0 and 1 from the base case conditions, and for every successive element I am calculating the sum of the previous two elements, right? So 2 will be 1, at index 3 it will be 2, at index 4 it will be 3, and at index 5 it will be 5. 3 plus 2, 5. So at the end I am returning this 5 dp of n. Okay, this is what tabulation is. Now if you observe carefully, when I was at index 3, the answer to the index 3 is depending upon the answer at index 1 and at index 2. Similarly, when I am at index 4, the answer depends on the answer at index 3 and answer at index 2. And very similar to this, the answer at the index 5 is dependent upon the answer at index 4 and answer at index 3. So I don't need to maintain this complete array. If I can maintain just previous two elements, I can get my answer, right? So we can optimize the tabulation approach further, and it is called the space optimization. Okay, so we will similarly have our function, and if n is less than equals to 1, we will return n, our base condition. What we will do is we will take two previous values, previous 1 and previous 2. Previous 1 will be 0, previous 2 will be 1. We get this from the base case condition. Okay, and then similarly to tabulation, we will run a for loop from i2 to n, and we can also have an integer current, and current will be the previous 1 plus previous 2. Okay, and after calculating the current, what I will do is I will shift these previouses by one step. So previous 2 will become previous 1 and previous 1 will become current. Okay, and at the end, what will happen when I reach the index n, my current will be my answer, and in for loop if you see, the previous one will also become the current, so I can return like current also or previous one also. Okay, so that's it for the space optimization, guys. Now if you look for the time complexity of the recursive solution, for every sub problem we are calling two recursive calls, so it is of order of 2 to the power n. For space complexity in the recursive stack, the maximum depth will be order of n, right? For f of 5 to f of 4 to f of 3 to f of 2 f to f of 1. Now for memoization, we are solving every sub problem only once. Okay, because we are having a check for this, and if we have already calculated a sub problem, we will return early. We will not make the recursive calls. Okay, so we are calculating every sub problem once. So that's why the time complexity will be of order of n, which is a huge optimization from the exponential time complexity of 2 to the power n, right? And then space complexity will be similar to the order of n. And for tabulation approach, we saw why the memoization is called top-down approach and tabulation is bottom-up approach, right? Next, we saw in the tabulation code, we will run a for loop which will run from 2 to n. So the time complexity here also will be of order of n. And for space complexity, we are again using a dp vector of size n, so it will be of order of n. But we didn't use the recursive stack here. Okay, and for our final approach, the space optimized approach, we again will have a for loop which will run from 2 to n. So time complexity will be again of order of n, and space complexity here, because we are having only two variables, so it's constant, order of 1. Okay, so the concept which we are using here is to remember the overlapping sub problems and all. This is what is called the dynamic programming. And we have seen how to solve a problem to make a recursive solution, then to memoize it, and then how to convert it into the tabulation form, right? And then from there, how to build the final space optimized solution. So that is all from my side, guys. I hope this helps. Let's meet in some other video. Till then, keep smiling, keep practicing. Thank you.